this setting. And it is possible to prove that sorry, I have not defined the domain. The domain EP, is a set of all densities which are connected to Q by an open exponential arc. So we have P, all the densities connected, called EP, E from exponential, I call it maximum exponential model. And these are mapped onto the interior of the proper domain of the cumulant function. So the cumulant function actually has a number of properties that can be taken from the property of the normalizing factor of the usual exponential family. And it is a convex function, is infinitely Gateau differentiable in the interior of the proper domain, and also it is analytic on the unit ball of the Oli space. And we have formula for the derivatives, precisely the derivative of k sub pu in the direction v is the expected value at q of v. The second derivative is a covariance at q. And the third derivative is the, let's say, three-way covariance of the three direction v1, v2, v3. So we summarize here the basic property we are using. The key statement is the following. I am using is the following. Q belongs to the maximal exponential family around P. Q and P are connected by an open exponential arc. The maximal exponential family around P is equal to the maximal exponential family around Q. And the logarithm of the likelihood, the log Q upon P, belong to both the Golding space. These conditions are all equivalent. And using that, we can write down explicitly the change of coordinates. And the change of coordinates is the restriction of an affine continuous mapping. Because we have u, the expected value of u, which is a linear function, plus a quantity which belong to both Oli space. And if we take the linear part, that is to say the derivative, we have the mapping u to u minus e q u, which is the centering of u at q. So, summary, we have the following situation. If P is connected to Q by an open exponential arc, then the two maximal exponential family are equal. And they are mapped to open sets SP and SQ. And there is a change of coordinates acting from SP to SQ. SP is embedded in a Banach space, B, I call BP, which is nothing less than the centering of the random variable in the Orlick space. And from BP to BQ, you have acting the derivative of the change of coordinates. So we have to talk talk now about the duality. So I'm going quite quickly here. Given a phi function, it's possible to define a conjugate phi function, and precisely my phi function is hyperbolic cosine y minus 1, whose conjugate is in the previous column, but I use it the more common equivalent function is up in red. There is a duality between these two spaces. This duality is continuous, and finally the space based on the dual function on the conjugate function as a dual, which is the exponential on a space. So there is a duality, there is no reflexivity, and our space doesn't have a dual described by functions, by the conjugate as a dual. Actually, it is possible to define a manifold on the dual system using simply as charts the likelihood minus 1. And this gives another manifold on P1 that is in some sense in duality with the original one. So I skip this. So if you want to define vector bundles, we have to define tangent space, and for example, we have to define what is a velocity of a curve. So I have defined two types of charts. In one chart, a curve p theta is represented by an element of the Orley space u theta, and to compute the velocity in this system, I have to take the derivative of u theta. And I have a second one where the representative is p theta upon p minus 1. In the first case, we have that the derivative, we do the obvious computation, the derivative of u is exactly the Fisher score dot p theta upon theta, but centered, because we want something with expected value at p0. So if we apply the transformation u from pt to p to the Fisher score, we get the representation in the exponential chart. In the second case, we have p dot p theta upon p fixed that we can transform from the Fisher score by multiplying by p theta upon p. That is applying a transformation I call um from p to the p theta. So the point is that the two transformation, if I take a reference at the point where I am, so a moving frame, I take I represent the derivative in the moving frame following the curve. The representation of the velocity is exactly the Fisher score. So in conclusion, the Fisher score is the velocity of the curve in the moving frame, and the Fisher information is the L2 norm of the velocity of the statistical model in the moving frame. That a useful interpretation to get the exact meaning of why the Fisher score is so important. So this leads to define two transport. I'm not talking about connection, and this is because many reasons. First, because talking about parallel transport and connection should be the same. And second, because I'm not quite sure which kind of differentiability we have to ask in this case, in this infinite dimensional case. Do we want Gateau, Fréchet, or continuous Gateau, or something else? I don't know. I'm not sure about that. And transport, in some sense, from the application point of view, I feel it is more natural. So we define two transport. One is a centering, the exponential transport. U goes to U minus the expected value in the new density. And the M transport is a multiplication by P upon Q. And these two transports are adjoint to each other in the natural duality. And the second derivative of the cumulant function, which is the covariance, actually can be identified with the operator consisting in applying first the exponential transport and then the mixed transport. These are all obvious formula in information geometry. I am rephrasing everything in this infinite dimensional setting. So what is a tangent bundle? A tangent bundle is a set of all PU, where P is a density, U is a possible velocity, that is to say a member of BP, and I give on this set the chart representing Q in the SP chart, and V, which is in the wrong tangent space, is transported to the right tangent space by the exponential transport. And this gives a manifold, and this manifold it's a tangent bundle. And in the tangent bundle, I can rephrase my computation of the velocity by saying that given a curve, I construct a curve in a tangent bundle by taking PT, delta PT, where delta PT is just a different name for the Fisher score. Using that, we can compute covariant derivatives. And, sorry, I go on. Here is an example of a possible computation in this setting. I fix P0, I take the divergence of Q P0, I represent everything in the exponential coordinates, I take the derivative at 0, and I have the formula for the covariant derivative. The covariant derivative in this case is in general the covariant derivative is an element of the dual of the Ornish space, so it's not a function. But in this case, it is a function because it is the logarithm minus the value of the divergence. So I have a formula for the gradient. the dual space I do the same. I define the pre-tangent bundle. By the same trick. Simply on the fiber I use the proper transport, which is a mixture transport, not the exponential transport. We can define the covariant derivative. And now, what about the Hilbert structure? So the Hilbert structure is usually obtained this way. We take the embedding of P into the sphere of the Hilbert space by taking the square root. So we have a mapping E from our manifold to L2, which is regular. I can compute the tangent space, and I can compute the tangent of the embedding. The tangent is 1/2 V square root of P. Is a tangent in the direction V, which happens to be a mapping from a regular mapping between Hilbert spaces. So how do I define a parallel transport in this case? Well, I pull back, and this again is not my idea, of course. I pull back the transport from the sphere, which consists of taking an element of the tangent to the sphere and transport it to another element, or to a tangent in a different position, by taking the orthogonal component equal and rotating the component in the plane given by the two vectors. And we have an explicit formula. Then we can move this back to our structure, and we get this formula. So this formula is an isometry from HP to HQ. HP being the Hilbert space of centered square integrable random variable at P. So this is an isometry. In particular, maybe this is an interesting application. If U1 UN is an orthonormal system, we can transport it in an orthonormal system in another space by applying this operator. And then I define the Hilbert bundle by using my transport. Again, the point is represented in the exponential coordinate, and on the fiber I apply the transport to make the trivialization of the bundle locally. Well, it is possible to write, there are this famous formula from Amari and also Hessian geometry, connecting the different connections. And actually in this, it's difficult, but in this framework it's possible to work out the relation between this transport and the other transport. Work in progress. So finally I summarize the constructions this way. So how do we construct a metric derivative? So H of P is the Hilbert bundle. At each P I attach the L2 space corresponding. Then we have L phi P equal phi Q. We have a transport between all the possible fibers, which are all different. And every everything is embedded in the space of measurable function. In this case, in this way, we get a covariant derivative. So what would I like to do with that? So here is not a theorem. It's a theorem, question mark, question mark, question mark. It's a problem. I want to solve differential equations. I have a representation in the moving frame of the derivative, which is a Fisher store. And if I am given a vector field f, the equation would be of the form which is written: Fisher store plus value of the vector field at p equals 0. This is a differential equation. For example, heat equation should be of this form, because heat equation works on densities. Boltzmann equation should be of this form, and so on and so on. And nonlinear filtering equation should be a differential equation of this form, one step up. Now, this is an infinite dimensional differential equation, and as far as I know, in infinite dimensional differential equation, we have to work exactly usually with the duality, and we have to ask the conditions, for example, the vector field to be maximal monotone. So, if you want, this is a direction of work. I am out of time. Do I have 5 minutes or not? Okay, the formed exponential. Here I am using quite freely ideas from many people, some of them in this room, without quoting anybody, so please forgive me. So the point is the following. I have an Hilbert bundle. I have a tangent bundle, I have a pre-tangent bundle, which are real tangent bundles, and I have a Hilbert bundle, which is not a tangent bundle. So is it possible to construct something such that the Hilbert bundle is a tangent bundle? So it has been suggested to move from the exponential family to the formed exponential family. There are many possibilities. Here I have an example which is a special case of a deformed exponential in a family called the Kaniadakis exponential. So you see is a function of shape similar to the exponential but quadratic growth. And it's possible to compute the inverse function. And there is a nice formalism introducing a chi function. In this case, it's this one. The chi function is controls the logarithm and the exponential at the same time. Now, what do we do? We do the following. We want to construct that the space we have defined is made of functions which are integrable with respect to a transformation of the original density, chi p, usually called escort density. So in this case, what happens? our exponential is equivalent to a quadratic function, and so our space, at least for p equal 1, in this case, is just the L2 space, which is very handy. We can define the connection by putting again the logarithm of the densities inside, and we can define the equality of these spaces for connected object. And for example, with p equal 1, which are the densities which are connected in this example? And these are the densities such that p and 1 upon p is integrable. So which is somehow a strange condition. So in some sense we have the ingredient. We have all the densities which are connected, where the space are equal, and the space being an L2 space. So there is some hope it is possible to work out a full theory of the exponential family in the form we have here, u minus the constant plus the logarithm of the reference density inside. And with this setting, the normalizing constant is a divergence of this form, and u is defined as we had before. Sorry, I'm late. Thank you very much.